Right, my name is Razi. So today we are going to do tutorial how to solve a problem related to cascade refrigeration system. Okay, so straight forward to the question here. Consider a two-stage cascade refrigeration system operating between the pressure limits of 0.8 and 0.14 megapascal. Okay, so I'm highlight here 0.8 and also 0.14 megapascal. So this is basically your upper limit of this cycle. Okay, and this is your lower limit 0.14 MPa. Right, each stage operates on an ideal vapor compression refrigeration cycle, okay, with refrigeration 134A as the working fluid. Okay, so this is the typical refrigerant that we use, refrigerant 134A. Okay, and highlighted here. And also it works based on the ideal vapor compression cycle. Means that there is no isentropic efficiency on the compressor. Heat rejection from the lower cycle to the upper cycle takes place in an adiabatic counterflow heat exchanger. So because this is a cascade refrigeration cycle, it combines, okay, ideal vapor compression cycle together, and then when it combine, we need to use another equipment we call as heat exchanger in order to transfer the heat from lower cycle to upper cycle. Okay, so here it states the heat exchanger is the place where both streams enter at about 0.32 megapascal. Right, so this 0.32 megapascal basically is your intermediate pressure where the heat exchanger is operate. Okay, if the mass flow rate of the refrigerant through the upper cycle is 0.05 kilogram per second, determine A, the mass flow rate of the refrigerant through the lower cycle, B, the rate of heat removal from the refrigerated space, and the power input to the compressor, and the last one is the coefficient of performance or COP of this cascade refrigerator. Right, so before we going to solve this problem, we need to understand the question, okay, based on the statement given here. Right, so I'm going to write the upper limit, okay, of the cycle 0.8 megapascal. So this basically is your the highest pressure inside your cycle where it is operated in your condenser. Okay, right, operated in your condenser. Okay, while the lower limit is 0.14 MPa. Okay, so this pressure is located at evaporator. It operates at evaporator because the evaporator operates at the lowest pressure in your cycle. Right, another pressure which is 0.32. Okay, right, 0.32 MPa operated in your heat exchanger. So we call this as intermediate pressure. Okay, so I want to say sorry this because my handwriting is not so good. Okay, so I hope that you understand. Okay, right, this is at your heat exchanger. Right, so what we are going to do with this pressure is we can set this pressure and try to sketch your TS diagram first. Okay, so before this, we know that the ideal vapor compression cycle, okay, must have at least two pressure limit. Okay, the first or the lowest pressure operate at evaporator, while the highest pressure operated at the condenser. Okay, so this is your ideal vapor. Okay, so I'm trying to review back, okay, on your TS diagram. Right, so we have here, right, okay, 1 2 3 4. Okay, let's say this is your step 1 2 3 and also 4. Okay, if we want to combine two ideal vapor compression cycle together, this we call as cascade. So how to put another cycle into your first ideal vapor compression cycle? We put on the upper limit of your previous cycle. So we just to sketch another ideal vapor compression cycle. Okay, so this should be your lowest pressure. Okay, operated at evaporator. Another TS diagram. Okay, located at the condenser pressure. Right, so to combine it, we put this into this. Okay, so this we call as cascade. Right, so I'm sketch bigger here, not so straight, sorry. Okay, right, so how to put this into this? We put here. So I'm just copy ideal vapor compression cycle and put in your cascade refrigeration cycle. Right, so this is state number 1, state number 2, state number 3, and also state number 4. Right, so this is your lowest pressure, which is 0.14 MPa. Okay, 0.14 MPa. And then I copy another one here, put here on the upper side. So here, okay, 1. Right, this should mean state number 5, 6, this is 7, and this is 8. Okay, so both cycle operated on counterclockwise direction. Okay, where it start from the compressor and then it goes to the condenser, expansion valve, and the last one is evaporator. So where actually the heat exchanger located? Right, it located at the condenser from the first or lower cycle, and also evaporator of the upper cycle. So if you want to make it clear, I can sketch the schematic diagram. So the schematic diagram basically purposely to make clear what the question asked about. Right, so these two diagram, schematic diagram and also TS diagram, is compulsory when you want to analyze the question. Okay, so I'm going to sketch your schematic diagram. So this is your TS diagram. Okay, this is your schematic diagram. Right, the first component here is your evaporator. Right, and then your compressor. Okay, right. I should draw lower. Sorry. Okay. Evaporator. Okay, this is your compressor. Then your condenser. This is your expansion valve. Okay, so this is your from the lower cycle. Okay, so refer to your lower cycle. Okay, where is your state number 1? Here, compressor. Then become state number 2. Okay, pass the condenser, become step number 3, and then pass through the expansion valve, become step number 4. Right, so this is lower cycle, and then we copy the same cycle and put on your upper cycle. Okay, so this is your evaporator. This is your another compressor. And then this is your condenser. Okay, and the last one is expansion valve. Okay, so it's 5, 6, 7, 8. So question here, student always ask, where is the heat exchanger position? Okay, so basically the heat exchanger is the combination of the first condenser in the lower cycle here and the combination of evaporator from the upper cycle. So this both component, okay, is built in one compartment. We put it in one compartment and it becomes heat exchanger. Okay, it's a big heat exchanger. Okay, so it becomes heat exchanger. Okay, so what you must to understand is the heat exchanger is the combination of evaporator and also condenser. Okay, the condenser from the lower cycle, the evaporator from the upper cycle. So hopefully you can understand both TS diagram and also schematic diagram. Okay, because after this, these two diagram is important when we want to refer to our state, right? So the first step to solve this problem after sketch these diagrams, okay, is to find the enthalpy of each of the state 1, 2, 3, 4, 5, 6, 7, 8. Okay, we have 8 states here. Without looking at the question A, B, and also C. So this is your first step. Find the enthalpy. So make sure you have master the property tables, because we need a lot of exercise on this property table. Okay, so we start with step 1. Step 1. Okay, so before we going to go for your property tables, okay, we must understand what is the state from state 1 until state 8. Okay, so from state 1, it exit the evaporator. So the refrigerant pass the evaporator to change its state from liquid into your vapor. So here at state 1, it becomes saturated vapor. Right? Saturated vapor. Okay, so it means that it is fully vaporized. Okay, so if it not fully vaporized, it becomes still a mixture. From liquid to vapor, it becomes mixture. But when we design or engineer design this cycle or refrigeration cycle, we must make sure that the evaporator length is long enough so that the liquid, all of the liquid change into vapor. So the first step should be saturated vapor, and then to find the enthalpy H1, it must equal to your Hg at that pressure. Okay, so what is the pressure? We refer back to your Ts diagram, right? So your evaporator pressure is 0.14 megapascal, okay, while your intermediate pressure here, which is state 2, state 5, state 8 and also state 3, okay, all of them is 0.32 megapascal, okay, 0.32 MPa. Right here, and the highest pressure should be 0.8 MPa. Okay, so your lowest pressure at state 1 is 0.14 MPa. Okay, so we need to go on your property table. So let's check out your property tables here, right? So your property tables, we need to look at the saturated table, saturated table. Right, so this should be 0.14 MPa equal to 140 kilopascal. So it should be here, but make sure you use saturated refrigerant, right? So this is saturated water, so I make mistake here, sorry. We need to look at the saturated refrigerant, so it should be on your next table, right? Refrigerants. Okay, so A11, A11 is your saturated refrigerant, so don't make mistake, okay, because it will give a very different amount on your enthalpy if you use wrong table. Okay, so look at the 140, right? 140 kPa. Okay, I can use this A11, or I can use A12. Okay, so if you use A11, you will get a round number of based on your temperature. Okay, it's like nice number, right? But if we want to refer on your pressure, better we look at the pressure, pressure, which is A12, round number 60, 70, and then our interest is to find enthalpy at 140. Okay, sorry, 140 here. So use your ruler, okay, or you can sketch here. Find your enthalpy. So your enthalpy for saturated vapor at 140 kPa should be 239.16 kilojoule per kilogram. Okay, so 239.16 kilojoule per kilogram. Okay, I am right. 239.16, okay, 16 kilojoule per kilogram, right? So this is your first state enthalpy. So we have another 7 state, another 7 state. So this is a tedious work. So we just follow. Make sure you do faster than me on your test or exam. Right, state 2. Okay, state 2. We want to find enthalpy at state 2. But first we need to know the state. the state. So what is the link between 1 and 2? It passed through the compressor, and we know that in the compressor, because this is ideal compressor, it works based on isentropic process. Okay, so you must know what is isentropic. It's a combination of reversible process and also adiabatic. Okay, right? Otherwise, it's not an ideal vapor compression cycle. It may be actual vapor. Okay, so the interesting about isentropic process is that one properties, which is entropy, which is S, is equal before and after the compression process. So in this case, we can write here S1 equal to S2. Okay, so we can write here, is to find H2, we need to know S1 equal to S2. Okay, so the amount of S2 is based on your state 1. So you need to find S1 first. So S1 equal to your Sg at 0.14 MPa. Okay, so to find your entropy on your first state, we go back to the same table, okay, and also same line because it's same state, and look at the next column, which is entropy. So look at Sg, right? Sg here, okay, because it is saturated vapor, and I take this amount 0.94456 kilojoule per kilogram dot Kelvin. Okay, I'm right here. Forgot already the number. 94456. 0.94456 kilojoule per kg dot Kelvin. Okay, so and then I'm copy back here S2 equals to 0.94456 kilojoule per kg dot. Okay, so after we get S2, to determine the state 2, we need another one properties, because based on state postulate, we need at least 2 intensive properties. Intensive properties means that the properties on your property tables here, the pressure, temperature, specific volume, internal energy, enthalpy, entropy. Okay, so we only get one properties, which is S. Another one is we look at the operating pressure at state 2. What is the P2? Okay, so here state 2, state 5, state 8, and also state 3. Okay, here 5, 2, 8, and also 3. All of the state operate at the same pressure, which is intermediate pressure, and the intermediate pressure operated inside the heat exchanger. So we should use the heat exchanger pressure, which is 0.32 MPa. Okay, so now we get these 2 intensive properties, entropy and also pressure. We need to name it state. Okay, so to find to name it state, we need to go back to property tables. Okay, property tables here. Look at pressure first, 0.32, 320 kPa here. Okay. Make sure you always refer to saturated table before name it state. This is your first step. Don't just jump into the superheated table here, A13. If you have named its state as superheated, but if you did not know what is the name of this state, you should go first on your saturated refrigerant table. So now my state 2 pressure is 320 kPa or 0.32 megapascal, and our entropy at state 2 is 0.94456. Okay, 94456. So here, to name its state, we need to compare the value of SF, and also SG. SF and also SG. So our value is 0.94456, right? Okay. So which is higher than SG? So what it means, if we get higher than SG, means that the name of its state should be superheated refrigerant table. So we write on our state 2 is superheated. Okay, superheated refrigerant. Okay, superheated refrigerant. And then to find the enthalpy, we should use superheated table. Okay, we should use superheated table. So go back into our property tables. Okay, and then search for superheated refrigerant. So here, right, superheated refrigerant. So to find the enthalpy, we need to search another properties, which is 0.32 MPa, okay, and also 0.94456 kilojoule per kilogram dot Kelvin for its enthalpy, right? So I'm go again for your superheated refrigerant table, searching for 0.32 MPa. Okay, here, right, 0.32 MPa, and then searching for another properties, which is entropy. Okay, entropy on your last column on this 0.32 megapascal table. Okay, right here, 0S. Right, so now when we want to search 0.94456, we could not find the exact value of 0.94456. So what we need to do is we need to interpolate the value between the nearest value. Okay, so 94456 located between 0.9301 and also 0.9544. Okay, so we need to interpolate between these two values, 9301 and also 9544. Okay, and then we need to take entropy and also enthalpy value, because our interest is to find what is the enthalpy for 0.94456. So I'm copy again this number 251.88, and its equivalent value for entropy is 0.9301, and then I take 258.69, and the equivalent value for entropy is 0.9544. Okay, and then I take this number and build a simple table for interpolation process. Right here, you can build simple table between entropy and also enthalpy. This is your enthalpy, this is your entropy for 0.32 MPa. Okay, 1, 2, 3. Right, so I'm just copy the number in your property tables, 251.88. Okay, and then the equivalent value is 0.9301, 0.9301. Okay, and then copy again the lowest 258.69, 258.69. Six is, and then the equivalent value is 0.9544, 0.9544. Okay, so our entropy for state 2 is 0.94456. Okay, 94456. So this interpolation method, the objective is to find its equivalent enthalpy for this entropy. Okay, so how it is done? Okay, it's very simple. You just copy row by row. Okay, and do this. Hash minus 251.88, okay, divide by 258.69 minus 251.88. So this is your first, this is your second. Okay, and then I'm copy the same parts here. Okay, this is your one, step 1, this is your step 2. Okay, so equal to, you take your first part 0.94456 minus 0.9301 divide by 0.9544 minus 0.9301. Okay, so using your calculator, you will get the amount of H2 equal to 255.95 kilojoule per kilogram. Right, so if you want to check your value whether it is correct or not, you can check here. Your value should be lies between 251.88 and also 258.69 kilojoule per kilogram. So now we have done two steps. So it's very tedious process. I'm sorry, but this is the question it asks, so it cannot be helped. Right, now we move to state 3. State 3. Okay, sorry. Right here, state 3. Okay. The state 3 basically exits the heat exchanger, where the heat exchanger consists of condenser from the lower cycle. So inside the condenser, basically the condensation process occur, where all of the vapor from our compression side here turn into liquid after the condensation process. Okay, after the condensation process. So after it exit the condenser, if it is fully condensed, it will turn into saturated liquid state. Saturated liquid state. So basically state 3 is saturated liquid because all of the vapor is fully condensed. So state 3 is quite straightforward other than state 2 because state 3 is saturated. Now to find H3 from the saturated liquid, we go back into saturated liquid table. Okay, saturated liquid table. Okay, to find the enthalpy, we must first know the operating pressure. Okay, the operating pressure P3 equal to heat exchanger pressure, which is 0.32 MPa. So on your saturated table, 320 kPa, right here. We're searching for value of SF, while SF, because this is saturated liquid, okay, so that's why we use SF, and we take this value 0.21637 kilojoule per kilogram dot Kelvin if this is your entropy. But our interest here is to find enthalpy, so the enthalpy here is HF, which is equal to 55.61 kilojoule per kilogram. So I'm writing here H3 is equal to 55.16 kilojoule per kilogram. Okay, so 55.516, right? And then after we get the enthalpy for state 3, we jump into state 4. Okay, where it will going to the throttling process, from 3 to 4 throttling process, where one characteristic of throttling process is we get the same enthalpy from 3 to 4, H3 equal to H4. This is for throttling. Or we got the expansion in the throttle expansion device. Okay, so very simple here to find the enthalpy. H4 equal to H3 equal to 55.16 kilojoule per kilogram. Okay, so here we have done for the lower cycle. Now the next process is to continue on your upper cycle from state 5 to state 8. Okay, okay, state 5 to state 8. Okay, state 5 here, it quite similar between upper cycle and also lower cycle, upper cycle and also lower cycle, because it is still a ideal vapor compression cycle, which is copied. We copy together and then put on your upper side. So state 5 basically quite similar with state 1 from the lower cycle, because here state 5 exit the evaporator inside the heat exchanger. So when it exit the evaporator, state 5 should be saturated vapor, because all of the refrigerant change into the saturated vapor. So to find the enthalpy H5 here, we should use H5 equal to Hg at its pressure, corresponding pressure. So H5 here, the corresponding pressure 5, because it is located inside the heat exchanger, so the pressure is 0.32 megapascal. Okay, 0.32 megapascal. So we go back into our property tables. Okay, saturated table 0320 kPa, and then find the Hg. Okay, Hg. So this is your Hg, right? Quite messy here. I'm erase all the unnecessary things. So 320 kPa, and then searching for Hg. So your Hg should equal to 251.88 kilojoule per kilogram. Okay, 251.88 kilojoule per kilogram. Okay, very easy. Now go for state 6. State 6. Okay, when the refrigerant change into saturated vapor at state 5, it pass through the compressor. Okay, here, and then become state 6. So what you need to know inside the compressor is still same between the upper and also lower limit, isentropic compression process, because this is ideal cycle, isentropic compression. So what you need to write here is the entropy S5 equal to S6. Okay, so to find H6, you need to name its state, but because we did not know what is the name of its state, we need to refer to your table. Okay, but to refer to your table, we need at least 2 intensive properties. Okay, so the first properties that we can get from the question or from this problem is at state 6 we have the corresponding pressure is 0.8 megapascal. Okay, so this is your property, or the highest pressure, 0.8 megapascal, located at the condenser. Okay, so we write again, H6 P6 0.8 MPa. Okay, while S6 equal to S5. So S5 is equal to Sg at 0.32 MPa. Okay, so this is quite straightforward. Okay, the same row, we look at your Sg value here. Sg value, because this is saturated vapor, and take this value and write in our sheet here, 0.933006, 0.933006, 0.933006. Okay, check again, 93006. Okay, okay, 0.93006 kilojoule per kilogram dot Kelvin. Then we look again these 2 properties. Okay, at your saturated table. Okay, 0.8. Okay, right. I think I make mistake here because S6 is 0.8. Okay, so we need to look at 0.8 megapascal rho. Okay, so what we are doing just now is 0.32 MPa. Okay, so better we check again. So this is 800 kPa, which is equal to 0.8 megapascal, and then okay, compare the value of entropy and also pressure. So S6 equal to S5, so this is correct. Okay, 93006, because we refer to state 5. Okay, state 5 entropy. Okay, 0.93006. Okay, hopefully you can understand my handwriting. Right, so we compare these 2 properties in your property tables S6 and also P6, 0.8 megapascal, and also S value. Our S is 0.93006. Sorry. So it was found that our entropy is higher than Sg. So it means that our state name is superheated vapor. So it becomes superheated vapor, right? So I'm writing here superheated vapor. So to find enthalpy at state 6, okay, we should refer to superheated table. Okay. So this is saturated table, and search for superheated table, and then searching for your corresponding pressure, which is 0.8 megapascal. Okay, 0.8 megapascal, and then compare or searching for your entropy value, which is 0.93006. It is located between 0.9183 and also 0.9480. Okay, so same procedure we need to interpolate, but this time I will not show you how the interpolation process is done. Okay, I'm just write the answer H6 equal to 95.48. Okay, 95.48 kilojoule per kilogram. Okay, right. Check again. 95.48. Sorry, not 95. It is 274.49 kilojoule per kilogram. So if you want to check your value, you must look at this. Okay, it must be located between 267 and also 276. So our answer is 274, which is correct. Okay, so this get from the interpolation method. Okay, now we move to state 7. Okay, state 7, it passes through the condenser and it becomes saturated liquid after it fully condensed. Okay, so normally for ideal vapor compression cycle, we must know that all of the process must obey ideal process. So this process is condensation, and when it passes through the condenser, we assume that all of the vapor is condensed, become a saturated liquid. So to find its enthalpy is equal to HF at its corresponding pressure. Okay, so look for your state 7 where it is located. Okay, past the condenser, so it means that the corresponding pressure is same, 0.8 megapascal. Okay, so 0.8 MPa. Okay, so to find the enthalpy, we go for your property tables. Look at your saturated table. Okay, saturated table, 800 kPa. Okay, searching for your HF, HF here, which is equal to 95.47 kilojoule per kilogram. 95.47 kilojoule per kilogram. Okay, when it is done, we can go for state 8. Okay, state 8, Very simple, because from 7 to 8 it passed through the expansion valve. Okay, and we know that when in the expansion valve, the enthalpy is constant, because it is throttling process. Okay, throttling means that we drop the pressure without losing any energy in terms of enthalpy. So this is throttling process. H8 equal to H7, 95.47 kilojoule per kilogram. So if you want to check whether state 7 and state 8 have different pressure, so look at our TS diagram. So here, from 0.8 megapascal, it dropped to 0.32 megapascal. Okay, so now we have done all of the 8 processes. Okay, 8 processes. So now we start to look at the question A, B, and also C. Right. So go back into your question A. The mass flow rate, the mass flow rate of the refrigerant through the lower cycle. Okay, to the lower cycle. So based on the information given, we have used 0.8, 0.14, 0.32 megapascal. The last information that we haven't used is the mass flow rate of the refrigerant through the upper cycle, which is 0.05 kilogram per second. So I'm sketch again my refrigeration cycle, lower and also upper. Why the mass flow rate is different? Because it consists of different parts, different pipe, and it is not mixing together. So that's why it have different mass flow rate, and also we can use different refrigerant. Okay, so I name the lower cycle as m.A equal to 0.55 kg per second. Sorry, 0.05 kg per second on the upper cycle. Okay, upper cycle. .05 kg per second on your upper cycle. Here, this is your m.A, 0.05 kg per second. While on your lower cycle, m.B, this is your question asking for. Right, so how to find the mass flow rate on the lower cycle? We need to use the special characteristic of this cascade refrigeration cycle, which is inside the heat exchanger. So what happens inside the heat exchanger? Basically, the heat is exchanged from the lower cycle to the upper cycle. Okay, so this is the process flow. So I am right here from state 2 to 3. Okay, this is state 2, this is state 3. And from the upper cycle, it is state here, I am refer here, from state 8 to state 5. Right, so this is the important part. The mass flow rate pass through the lower cycle m.B, and then for the upper cycle is m.A equal to 0.05 kg per second. So the process occur inside this heat exchanger is the heat is transferred from the lower cycle to the upper cycle. Okay, Q. And if this heat exchanger is operated at 100% efficiency, and then there is no heat loss, okay, to the surrounding. So we assume that all of the heat from 2 to 3 is transferred to heat from 8 to 5. So what happened here is Q dot 23 equal to Q dot 85. Okay, 2 to 3 and then 8 to 5. So what is the heat equation? It is based on the mass flow rate times the enthalpy change. H3 minus H2. Okay, mass equal to m dot H 5 minus H 8. Okay, so the mass flow rate at the lower cycle is m dot B, and for upper cycle is m dot A. So we use this equation to solve the problem and then find the m dot B, which is the mass flow rate for the lower cycle. So I'm rewrite again, m dot B, H3 is 55.16 minus H2 255.95 equal to m dot A 0.05 H5 minus H8. H5 is 251.88 minus H8 95.47. Okay. And then when you want to solve the equation, okay, H5 I check again, H3 minus H2. Okay, 3 minus 2, H3 is 55.16, and then H2 is 255.95 kilojoule per kilogram. H5 is 251. Okay, and then H8 is 95.47. Okay. Right. Okay. So here, sorry, because this is heat transferred out, this is heat transferred in. So this is in, this is out. So your equation flow is different, right? So this is Q out, means that you need to use equation m dot H in minus H out. While for Q in, okay, where the heat is absorbed by the evaporator, the equation is m dot H out minus H in. That's why here is okay, m dot A H5 minus H8, while for Q dot 23 equal to m dot H in minus H out. So I write here m dot B. In is H2 minus H3. So the value here is opposite, right? 255.95 minus H3. H3 is 55.16 kilojoule per kilogram. 55.16. And then when you solve this equation, you get the value estimated to be around 0.039 kilogram per second. Right? So This is your first answer for first question. And then let's check for question B. Question B is the rate of heat removal, okay, from the refrigerated space and the power input to the compressor. So you need to understand carefully what is the question M4. The rate of heat removal from the refrigerated space. So it means that if you have refrigerated space, it will absorb by the evaporator. What the question asks for is your Q dot in. Q dot in from the refrigerated space to your evaporator. And the same question is power input to the compressor. Power input is very straightforward because we have two compressor, means that we have 2 times compression process. You need to add together. So it asks for Q in. Okay, Q in from the evaporator. Q dot in. So the Q dot in, basically we need to check at your schematic diagram what is the state related here. So the heat is absorbed by the evaporator, and then the refrigerant flow from state 4 to state 1. Okay, so to calculate the Q in, basically we need to use equation Q dot in equal to M dot hash out minus hash in. So your equation becomes M dot. What is your M dot here? On the lower cycle we use M dot A, okay, M dot B, hash out is hash 1 minus hash 4. So copy again, Q dot in equal to M dot B hash 1 minus hash 4. What is your M dot B? 0.039. hash 1 is 239.16. Okay. Hash 4 is 55.16. 55.16. So you got the value to be 7.18 kilowatt. Okay. So your unit must be consistent because this is kilojoule per kilogram, while your mass flow rate based on kilogram per second. And when we multiply this together, it becomes kilojoule per second, or simply we write as kilowatt. So this is your second question. And then for the same question, also second question, we need to write the power input. Okay, power input for the compressor. So because we have 2 compressor, we need to add the compression process from lower cycle. Okay. And also the power input at the upper cycle. Okay. So what is the equation for power input? It is based on the mass flow rate, M dot hash out minus hash in. Okay. Hash out minus hash in. This is W dot in. Okay. So we do one by one. W dot in equal to, for lower cycle we use M dot B. Your hash out is state 2. Okay, we look at the compressor. Out is hash 2 minus hash 1. Okay, hash 2 minus H1 plus the power input for upper cycle, we use mass flow rate m dot A, and then the H out for the upper cycle on your compressor side is H6, and then the input is H5. H6 minus H5. So you put the value 0.039. H2 is 270. Sorry. 255, 255.95. 255.95 minus H1. H1 is 239. 16 plus m dot A. M dot A is 0.05. H6. H6 is 274.49. 274 minus H5. H5 is 251.88. Okay, and then you put the value together. Okay, you will get the answer estimated around 1.6 kilowatt. Okay, 1.6 kilowatt. Right. Okay. Now we look for the last question, C, which is we want to calculate the COP. So the COP is very straightforward question, which is the performance of this refrigerated cycle. Okay. COP equal to Q dot in or Q dot L, okay, which is your refrigerated space, from your refrigerated space divided by power input. Okay. So from the value from the previous two question, your Q dot L is 7.18 kilowatt divided by the power input. Power input is 1.6 kilowatt. So you got the value should be 4.5. Okay, 4.5 or 4.4 of COP. Okay, so normally the COP must be greater than 1 for all of the refrigeration cycle, and using this cascade refrigeration cycle, you have better COP. Okay, and also it is very suitable for a large range of temperature. Right. So this is the end of this question. Hopefully you understand all of the steps given inside this tutorial. Hope to see you again. Bye.